Okay. Right. Okay. This is lesson 2.5, continuing, proving a sequence converges. And here we have a sequence that starts off with 1, and then negative 1/2, and then 3, 1/3, and then negative 1/4, and 1/5, and it goes on through forever. So notice that it's positive, negative, and it keeps getting the denominator keeps getting larger, the fraction keeps getting smaller. So it's converging to a point. So the equation for this sequence, a to the n, is a -1, a quantity of -1 with n plus 1 as an exponent over n in the denominator, where n is 1, 2, and it goes on. So we can say that this is going to be the sum of a to the n, where I is, where n, this should be n, where n equals 1 to infinity. So if we were to graph this here at 1, when n is 1, we have 1. And then the value is 1. And then 2, the value is negative 1/2. And then 3, the value is positive 1/3. 4, the value is negative 1/4. 5, positive 1/5, and so on. And so on. It keeps going and going and going. So it's converging to a limit. So we want to find this boundary to where we can say, all right, this sequence eventually gets inside epsilon, the value epsilon. And so we're trying to find where do we set that boundary uppercase n. Last time we used n, this time we'll use uppercase n. So from that, our proof is that the limit as n approaches infinity for a to the n, which is -1 n plus 1 over n, we want to find, we're saying that equals 0. Okay, if and only if, first we have to define. So our definition, we have to define our proof, what we're going to prove here. We have to define it. So for all epsilon greater than 0, there exists an n, all n, our limit, where we're going to set our limit, is also has to be greater than 0, such that our sequence n, 1, 2, and so on, goes on to infinity, has to be greater than whatever our limit uppercase n is, where we're going to set our boundary. Then we have our absolute value. Instead of f of x, we're using our sequence. A of n, the difference between our sequence and our limit is less than epsilon. So we're talking about we want it to be within this epsilon boundary here, because that's what's gonna, the narrower that epsilon is, the closer it is to get to our limit. So so this right here, a to the n minus L, that's the distance between our sequence and the limits. So as our sequence goes towards infinity, this difference is going to get smaller and smaller and smaller. And we want it to get small enough between our sequence and our limit, which is 0. So the distance between the sequence is narrowing between our sequence and our limit. And we want that less than epsilon. So here's our epsilon. Limit plus epsilon and limit minus epsilon. So as this a to the n, as this distance is from a to the n to our limit gets smaller and smaller and smaller, it converges to our limit, okay, which is 0. Okay, so basically what we're looking for here is we're looking for n. All right, so let's see how we're going to do that. So basically, we start with this a to the n minus l. Instead of f of x minus l, we're using a to the n minus l. And we said that a to the n minus l is a negative 1 to the n plus 1 over n minus our limit, which is 0. And we're saying that has to be less than epsilon. Okay, so that's what we're working with here. So this a to the n minus 0, that's just going to be a to the n. So that's a negative 1 to the n plus 1 over n. So that 0, that just goes away. So that equals to that. So from here, we're saying, all right, because this oscillates between positive and negative numbers, absolute value is going to be all positive. So that means that this is just going to be 1 over n. Because this negative 1, n plus 1, that's what makes it go from positive to negative, because that n, when n is 1, it becomes squared, and that becomes positive. When n is 2, it becomes 2 plus 1 is 3, it becomes a negative, and so on. So now, we know that because it's absolute value, we can drop the negative 1, and it's just 1 over n. Well, because it's positive, we can drop the absolute value. And so that's just 1 over n is less than epsilon. So from here, we can just multiply n to both sides, multiply n, and so we get 1 is less than epsilon times n, and then we divide epsilon to both sides, and we get 1 over epsilon is less than n. Okay, well, if we flipped it, right, that'd be the same thing as if we said n is greater than 1 over epsilon. So all we did was just flip everything. 1 over epsilon is still on the small end, and still on the small end over here. Okay, so now what we're saying here for our proof is that for all epsilon greater than 0, we choose an n, our boundary, as greater than 1 over epsilon. And I'll explain why that is in a moment. Then for all n greater than our sequence n greater than our boundary n, we have our negative 1 to the n plus 1 over n minus, I'm going to do this in a different color so you can see it better. We have our absolute value of a negative 1, n plus 1 over n minus 0 is less than epsilon. is true. Why is it true? Because n has to be greater than whatever 1 over epsilon is, whatever epsilon is. Okay, so, and this is because n, our sequence n, is larger than our boundary n, and that's what we said over here. And that's greater than 1 over epsilon. So then n is, since n is greater than 1 over epsilon, then we can say the absolute value of 1 over n is less than epsilon. So basically what I'm doing is I'm working backwards. So this is like the scratch work, and then this part here is the proof. So from here, we can say, all right, well, that's negative 1 over n is less than epsilon. And that's going to be this, because it's absolute value, then that's negative 1 to the n plus 1 over n minus 0 is going to be less than epsilon. And so that's our limit, which makes this true. So we have our scratch work, and then once we figure out what our n is and our boundary n, then we can go back and state our proof. And so we have proven it, and that's